So now we've seen the predict not taken branch predictor, and we saw that it didn't work so well. Let's take a look at some other predictors that we can use and see if we can find one that works a lot better. So the predictors we're looking at now are what are known as static branch predictors. That is, they make a prediction for a branch and they never change it. So we're picking this once and we're keeping it static. So we've seen the predict always not taken one, and obviously you can always predict always taken. And which one of these is better is going to depend on how the compiler is generating code. Let's think about loops and see if there's a more clever way to predict what's going to happen. So in a loop, you go around and around the loop many times. And what that means is that the branch at the end almost always jumps back to the front of the loop, because this loop is repeating a lot. So we could have a predictor which takes advantage of that. So we could predict that backwards branches are taken and forwards branches are not taken, or BTFNT. So the idea here is that in a loop, when you jump back to the top of the loop, you almost always go around the loop. So jumping backwards, you should be taken, but when you're jumping forwards, you're probably leaving the loop, so you're probably not going to take it. How about the compiler? Can it help predict branches? Well, the compiler knows a lot about the program, so yes, it can help. So if the program can identify the likely branches, so if it can find loops that it thinks are going to run many times, or if it can find code that's checking for errors. Because remember, errors don't happen very often. So if the compiler sees an error check, it can put in a hint saying this branch is not likely to be taken. So how well do these predictors do? Here's branch predict and accuracy on a bunch of particular benchmarks, so slightly different numbers than what we saw before. And here's always taken and not taken, and they're not doing so well. Somewhere between 40 and 60% accuracy, depending on the architecture. So how about this backwards taken, forward not taken? Well, it does better. So we're up to about 65% here, but that's still not good enough as we saw in the previous section. How about adding compiler information? So with the compiler in there, we can do a lot better. Now we're up to 75% accuracy, but that's still not good enough. We need to do significantly better than this. And how can we do a lot better? Well, we have to stop using a static branch prediction, and we have to use branch prediction that learns what the branch is doing. And this is called dynamic branch prediction. So this is a part of the processor that learns what branches are doing and uses that information to predict what branches will do in the future. So if we look at how well they did, we can see they can do a lot better. So we're getting up into the 95–98% accuracy with these dynamic branch predictors. And that's now high enough accuracy that we can really keep most of the performance even in modern processors. So let's take a look at an example here. So what the branch predictor is going to do is the dynamic one is going to ask the question, did what we did in the loop the last time, is that going to help us predict what it will do this time? So use the information from last time, that is the history of the branch, to predict what it will do this time. So is this going to be a good idea? Let's take a look at some code. So here's a loop. We're going to go around 1,000,000 times and do something. Does what the loop did last time help us predict what it's going to do this time here? Well, absolutely. So 100 million times around this loop, we're going to do exactly the same thing. We're only going to predict it wrong once, and that's at the end of the loop. How about code like this? If A equals B, we do something, otherwise we do something else. Well, this code is a lot less clear. You could easily have code that every other time A equals B and the other times it doesn't. So maybe what it did before doesn't help you at all. Or you can have code where A equals B checks if there's an error. And there's almost never an error, so most of the time you'd only go one way, and then you could predict it. So it's clear that this history-based behavior is very useful for some branches, but might not be so useful for others. So let's take a look at some examples here. So remember, the idea here is to record what the branch did before, record the branch's history, and use that to predict what it will do next. So let's take a look at some examples. Here's a branch history, which is one not taken, followed by a whole bunch of takens. So based on this history, what's a reasonable thing to predict is the next branch? Well, it's reasonable to predict that it's taken. We have a whole bunch of takens in a row, so it's likely the next one is going to be taken as well. How about this pattern here where we alternate not taken and taken? Well, it's very likely here that the next branch is going to be not taken. There's clearly a pattern that goes back and forth. Here's a more complicated pattern, probably going to be taken here. Here's another history which may or may not be a pattern. So it looks like it's pretty likely that taken is going to be the next outcome, because we just had a whole bunch of takens in a row, but if it was a really long pattern, you could also have not taken. Similar for this one here. We just had 5 takens, but it looks almost like we have a not taken every 5 takens. So it could be taken or could be not taken. So you can get varying degrees of complexity in the patterns here, and depending on how much hardware you're willing to build in your processor, you can learn more and more complicated patterns. So what we're going to talk about next is how do we build something that will work this way. Here's a question about history patterns. Is not taken a reasonable prediction for the next branch for a branch history pattern that looks like this? Well, yes, it is a reasonable prediction. If the pattern is 5 takens and not taken, 5 takens and not taken, then the next one would be not taken. However, we just saw 5 takens in a row, so it's reasonable to think that the next branch will also be taken. What hint should a compiler give the hardware about whether a branch is taken or not for the following code? So the code is if, and we're checking an error, then we take the branch. Well, here the hint the compiler should give is not taken. If the compiler knows this is an error check, it knows errors are very rare, and so it's unlikely that we're going to go and actually handle the error because errors don't happen that often.